Hello and welcome to Podcast.init, the podcast about Python and the people who make it great. I would like to thank everyone who has donated to the show. Your contributions help us make the show sustainable. When you're ready to launch your next project, you'll need somewhere to deploy it, so you should check out Linode at linode.com/podcastinit and get a $20 credit to try out their fast and reliable Linux virtual servers for running your app or experimenting with something you hear about in the show. You can also visit our site at www.podcastinit.com to subscribe to the show, sign up for the newsletter, read the show notes, and get in touch. To help other people find the show, you can leave a review on iTunes or Google Play Music, share it on social media, and tell your friends and coworkers. A little bit of news before we start the show. I'm also launching a new podcast called the Data Engineering Podcast, which is about modern data management and data infrastructure. So if that's something that you find interesting, then you should go check it out and let me know what you think. Your host, as usual, is Tobias Macey, and today I'm interviewing Paul Kehrer about cryptography and encryption in Python. So, Paul, could you please introduce yourself?
Sure. So I'm Paul Kehrer. I'm Reaper Hulk on Twitter and other services like Freenode. And I work as a principal engineer at Rackspace Hosting. And for my day job, I'm involved heavily in encryption and security, which means that I spend a lot of time with the Python Cryptographic Authority writing Python software.
So how did you first get introduced to Python?
So I actually came from a Ruby background 4 years ago, and I was recruited over to work at my current employer, and they were a Python shop, and that was specifically to work on a Python project in the OpenStack community. And so I was basically crash coursed into Python and said, oh, you need to start doing a bunch of Python work, and you need to spend all your time working on security projects for that. Which, of course, led into my current status where I was looking at the ecosystem of Python cryptographic libraries and did not like what I found.
So can you share a bit of the background behind the Python Cryptographic Authority and how you got involved with it?
I guess that would have been 2013 at this point. So around August of 2013, I was looking around and not enjoying the state of cryptographic libraries in Python. And I reached out to Alex Gaynor and David Reed, who at the time were both Rackspace employees as well, although they've both moved on since then. And they had an idea of taking a CFFI-based project, which at the time was called OpenTLS, and basically rewriting it from scratch and seeing what we could do. So from there, we said, okay, we'll create a Python Cryptographic Authority, which is just kind of an amusing name at the time to play on the fact that Donald Stuft had recently created the Python Packaging Authority. And we were going to just keep working to try and build sane cryptographic defaults and well-tested software.
Yeah, I noticed the similarity to the Python Package Authority, and I spoke with Donald Stuft on a past episode. So I was wondering if there was any sort of standardized naming around that, where if there was a particularly significant attribute of the Python ecosystem, then somebody would create an authority around it. But it sounds like it was largely just sort of tongue-in-cheek.
Yeah, it was initially intended as tongue-in-cheek. I would say that at this point, actually, that the Python something authority has become almost exactly what you described, which is effectively that someone sees a gap and they go ahead and say, well, if I'm going to take this on seriously, maybe I am going to name it something like that. So most recently, I know that Sigma Virus, who's Ian, I'm sorry, Ian, I forgot your last name suddenly, but he recently started the Python Code Quality Authority to contain Flake 8 and some of the other, like Flake 8, PEP 8, and some of the other tooling that we use for doing code linting in Python.
Yeah, by having these Python blank authority, it serves a good purpose in that a lot of times when you're looking around at packages that are available, particularly in an ecosystem as large as Python, it can be difficult to understand what the canonical or sort of most well-supported offering is for a given use case. And so by having the Python Cryptographic Authority or the Python Package Authority, you can look at the projects that are held under that umbrella and say, okay, well, this is the best of breed for this particular thing. And as long as the packages that are held underneath those various authorities do continue to be best of breed, then it doesn't dilute the brand, and it can serve as it can serve its purpose as making it easier to understand where particularly beginners or even intermediate people should start in the process of selecting what to include in their projects.
Yeah, and I think that actually is a great thing, although one of the, as you noted, we have to stay best in breed. And since we're not sanctioned by any actual authority, the authority we have is derived from our name plus our track record. So ideally, we continue to operate with a stellar track record and make people continue to believe that authorities should be trusted.
So there's an adage that I've come across a number of times that you should never roll your own crypto because of the fact that there are a lot of potentially sensitive applications and serious side effects if there are bugs or exploits that are introduced into the implementation. So I'm wondering, what was the problem that the cryptography library was trying to solve that was important enough to disregard that particular warning?
Sure. So the adage to not roll your own crypto is generally a very good one, obviously. You can fail with crypto at many levels. Like most fancy level, the level you read about most often, crypto fails when people have subtle implementation bugs, like if they have their AES implementation, have a timing vulnerability related to the fact that it uses like a jump table to compute what they have internally. It's called an S box. And that can allow like key leakage. Those things can get super advanced, all the way from an example like that to doing power analysis to see if certain things, when you're doing an RSA modular exponentiation, like certain operations will take more power, and that allows you to determine which code paths are being taken, which can disclose the private key. So that's like the most subtle level of where you can fail at implementing your own crypto. However, there's like a much more common level and a much more concerning level for people in the Python ecosystem, and indeed most programmers. And that's that cryptography gives you like building blocks. A lot of the time people like to talk about them as Legos, but I think it's more accurate to describe them as Legos with razor blades taped to them. So you can compose things and you can build beautiful, amazing things, but there's a very good chance you're going to cut yourself repeatedly while doing it. So the reason, ultimately, that we created the cryptography library was to solve actually both levels of this. On the first level, at the base level, was that PyCrypto and M2 Crypto both had major issues when those were the dominant ones at the time. PyOpenSSL as well, although we now actually possess PyOpenSSL under the umbrella of the Python Cryptographic Authority. But PyCrypto is, while it's convenient to compile because it contains all the C code that you would actually need to write to be able to use the cryptographic primitives, it is all bespoke C. And what I mean by that is that it was all written just for PyCrypto, which means it's had limited attention. There have been quite a few CVEs, even in the recent past, all around the fact that like this is not looked at that extensively. So like this code has not been reviewed for those timing side channels. It hasn't been reviewed to see that it doesn't have certain types of buffer overflows. It hasn't been reviewed for all the sort of things that you would expect a crypto library that is in wide use to see review on. And then at the other level, we care deeply about trying to make the code have, or the API, we want it to be misuse resistant. And so API misuse resistance, to be clear, is a very active area of research within crypto right now. No one really quite knows what that genuinely means. But as programmers, we certainly have opinions about how people do misuse things and how we can prevent them from misusing them in those particular ways. So cryptography structure is largely geared around the idea that what we would like to provide is recipes that solve use cases for people. And those recipes limit your choices, but by limiting your choices, they also limit your possibilities of screwing up. Of course, we also recognize that the reality of crypto is that a lot of the times you're attempting to interoperate with legacy systems that did things in ways that are just super horrible. And so we also expose the layer that is dangerous. However, to make sure that it's very clear and easy to grep through your code base to see where you're doing dangerous things, we use the term hazmat. So whenever you import those things, you're importing from something deep in the hazmat module. And so just grepping through your code base for hazmat will show you where those dangerous areas may be.
Yeah, when I was looking through the documentation, I saw that it had all of the warnings and explicit notifications that if you do this, you are taking your own life into your hands and we are not responsible.
Yeah.
Yeah, namespacing it under the hazmat definitely, as you said, gives a good amount of visibility and makes it so that if you are trying to refactor those pieces out or if they are intended to have a limited lifetime, then it makes it easy to target those refactorings so that you can move it over to the quote-unquote safer side of the library.
Yep, and that's absolutely the goal. Of course, those things become aspirations, and they're not always things you achieve immediately. In the case of cryptography, one of the things we have not succeeded at yet is writing enough recipes. So we have a primary recipe which allows you to do authenticated symmetric crypto in a very safe fashion. But the nature of it, because crypto is not perfect, is that it's a one-shot encryption model. What that means is that you have to encrypt all the bytes at once and decrypt them all at once. And we won't show you any of the bytes until after we've authenticated that data is still good. Now, that's obviously the way you want it to work, but it means that you can't do things like encrypt 30 gigabyte files unless you have 60 gigs of RAM free.
Yeah. And stepping back a little bit, I just realized that we haven't really given a high-level overview of what exactly the cryptography library is. So if you can do a brief overview of that, and also maybe a little bit of how you came by your hard-earned knowledge of cryptography and how you first got started in that field.
Sure. So ultimately, cryptography is a library for providing encryption primitives and high-level recipes to developers in Python. It came about, and its purpose was to provide support in a world where Python 3 and PyPI were not commonly supported. We wanted to make sure that we maintained it well. We wanted to make sure that we had top quality implementations of algorithms, as in ones that don't have known side channel attacks and things of that nature. We wanted to have the high level APIs, as we kind of previously discussed. And we wanted to have modern constructs like AES GCM, hash-based key derivation, things of that nature. Finally, we wanted to have we wanted to make sure that our defaults were as good as we could make them and have good testability. On your other topic, which was, I guess, where I earned my knowledge, so to speak. So out of college, I started actually working with a certificate authority. So I spent the first 7 years of my career working on a globally rooted certificate authority and managing a public key infrastructure. So in the course of that, I learned a lot about the operational side of that, but I also continuously was required to learn more and more cryptographic defaults and where we could run afoul of various problems. And that led to kind of just a general interest. In general, most of my knowledge is self-taught, which is sometimes good, sometimes bad. Certainly, it's helpful from the cryptographic engineering side, but from the pure cryptography side, occasionally I do have cryptographers I reach out to explain to me papers that are beyond my understanding.
Yeah, the nature of cryptography and all of the theory involved is definitely rather daunting, the number of times that I've sort of made brief forays into it and tried to understand a little bit more at the fundamental levels what's happening, because there are a lot of complicated mathematics involved and sometimes unproven theories that are put into practical use, such as the sort of prime theories that are still in active research.
Yeah, absolutely. I mean, the cornerstones of modern cryptography right now, for asymmetric especially, right, are basically the prime factoring problem is assumed to be hard, and that's the basis of why RSA is functional. And then for elliptic curves, it's the assumption that the discrete log problem is difficult. Like, both of those are unproven. However, we have a high degree of confidence that they are difficult, but there have been breakthroughs in the past that have made certain things easier, right? So like the current state of the art in the world of prime factoring is the general number field sieve. And the general number field sieve has seen significant advances in the last decade. So like prime factoring is faster than it was before. It's getting faster than computers are getting faster.
Yeah, and then when quantum computing becomes a mainstream viable option for a computing platform, then we're all in trouble, and our cryptography will most likely be rapidly broken, and we'll have to develop all new techniques for trying to survive in a world of ubiquitous quantum computation.
Yep. So fortunately, academia is very interested in the concepts of post-quantum cryptography. So like that's PQ is the standard way they refer to that. So there are things like lattice-based crypto. Actually, Google Chrome recently ran an experiment where they did a TLS handshake, doing the initial key exchange using a post-quantum algorithm called New Hope. New Hope is a variant on a ring learning with errors based lattice. So there are lots of things currently in research for what we can do for post-quantum. And the reason that people are interested in it right now actually is that if you assume that 20 to 30 years from now, we're going to have functional quantum computers, then there are secrets being encrypted right now that we don't want to be decryptable 30 years from now. So we need to have PQ crypto available for at least some subset of use cases as soon as we can, because we want to be able to protect those secrets when those machines come online.
Not to scare everybody right now, but be aware. So given the sensitive nature of the libraries that you're working on under the Python Cryptographic Authority, what are some of the development practices that you rely on to prevent the introduction of vulnerabilities and verify that the existing code is safe from known attacks?
So there's several things we try and do. So all this is documented on cryptography.io under our development practices section. But one of the biggest items is, this ends up sounding very, very common, right? Like, well, we say, we care deeply about code review. Well, we certainly do. So as a part of that, anyone who submits a PR, someone else must review it. The author is never allowed to merge their own PR. If multiple people contribute to a PR, none of those people are allowed to merge. It must be a third party on that front. On top of that, we do coverage with branches using coverage.py, obviously, and we merge that across a very large fleet. So we have over 30 different builders on Travis CI, and then we have an additional 25 or so on a Jenkins instance. So if we don't have 100% coverage, and that includes branches, and we have no pragmas for marking lines that we don't check, then it's not mergeable. And then finally, because of that giant CI system, we have a lot of tests that run a lot of permutations across a lot of different platforms. Like right now, we run against OS 10, 10.7, 10.8, 10.9, 10.10, 10.11, 10.12. We also run against 7 Linux distros, and then we run on multiple Windows, including obviously both the 32-bit and 64-bit variants. Anything we say is supported is a thing we actually run in our CI. So that means we also run Python 2.6, 2.7, 3.3, 3.4, 3.5, 3.6, and PyPy versions, all in our CI and all against every platform. Now, that's obviously a very large combinatorial explosion when it comes to our test suite. In fact, last time I checked, I think we were somewhere north of 8 million tests every single time a commit is pushed. That can sometimes take a while.
I can imagine.
Yeah, but the core of it is obviously that, yes, we're very concerned about making sure that this stuff is correct. And we don't trust it. Like, the cryptographic primitives, in large part, are provided by an underlying C library. But we don't trust that C library to be correct, which means that we run insane amounts of test vectors. So anytime we land any new feature, say you added a new mode to AES, a component of that would be us saying, okay, we must find a set of official test vectors that provide sufficient numbers of permutations. And that's usually doing things that try and like exercise unusual corner cases of the way the underlying crypto library or crypto primitive works. So that sometimes can be a few thousand tests. In the case of GCM, which is actually surprisingly tricky to implement properly, we run over 50,000 permutations of tests against the underlying library.
Yeah, I noticed when I was going through the documentation that the primary linking for the cryptography library is against the OpenSSL library, which has had a number of high-profile vulnerabilities in recent years, including Heartbleed as being sort of the best-known one. So I'm wondering if it's possible to swap out that backend for alternative implementations such as LibreSSL from the OpenBSD folks or S2N from Amazon.
Yes, cryptography links against OpenSSL, as you noted. You can swap LibreSSL out, no problem. We do support that. It's an officially supported configuration. S2N actually leverages OpenSSL, which is always an amusing one for people. So OpenSSL is actually properly 2 separate libraries. When you build it, you get a libSSL and you get a libcrypto. So the one that tends to cause us all the trouble and the heartburn is libSSL. Libcrypto is just an implementation of all the underlying cryptographic constructs. So that's like Diffie-Hellman key exchange, elliptic curves, RSA, AES, those sorts of things. And those are actually highly, so let me be clear, while the API of OpenSSL is atrocious, those are highly respected implementations and generally are considered best of class, both from a security and a performance perspective. LibSSL has obviously had its share of challenges. So S2N is actually a re-implementation of libSSL effectively. It uses libcrypto for the underlying cryptography, but it writes its own key exchange. It does its own TLS state machine, things of that nature. Whereas LibreSSL was a hard fork of OpenSSL that allowed them to perform the sort of like major surgery they wanted to provide while maintaining almost API compatibility. Their original goal was to have API compatibility, but they have diverged somewhat at this point. Right now, you can swap out to LibreSSL for sure. Cryptography is designed with a backend agnostic model, which is to say that we've built it where we have interfaces that you can form to, and you can actually write arbitrary backends that use whatever crypto libraries you want. Actually, when you pip install cryptography, if you do so on a Mac, we have 2 backends, one of which is OpenSSL and the other of which is Common Crypto, which is Apple's underlying symmetric crypto primitives. So on that platform, you can use either.
And when there are discovered vulnerabilities in the underlying backends, are there any mitigating factors that you put into play to try to help people avoid exposing themselves to the effects of those vulnerabilities?
It depends upon the vulnerability. In general, it's very difficult to do that for a variety of reasons. One of the first thoughts you might have is that you would just say, okay, if we detect that we're running on top of an OpenSSL that's known vulnerable, we will, at least raise a user warning or something. But in practice, it turns out that distributions like Red Hat, Ubuntu, etc., they'll patch the vulnerability, but they won't rev the version because they're trying to maintain ABI compatibility with their existing install base. So that means that like just looking at the version of an OpenSSL is actually insufficient to know whether or not it actually is vulnerable to a problem. In fact, you need access to the underlying, like essentially the distro's package version, and that's not something you can access from the OpenSSL APIs. The unfortunate reality of the world right now is that in general, we have to assume that you are conscientious enough to upgrade when you need to. Now, in the case of Windows and Mac, we actually ship a statically linked OpenSSL as part of pip install cryptography, the idea being that you don't need to have a C compiler on those platforms, as long as you have a sufficiently new pip. Now, that means that we are the ones who are responsible for updating OpenSSL when it's out of date. So we are pretty good about that. We take at most 1 day, typically less than 1 day, to ship a new cryptography that links against the updated versions of OpenSSL. However, there is an outstanding problem, and this is one that we've been talking to with distro maintainers and with people, obviously with the PyCA as well, to say, like, when we have this sort of issue, how do we tell people that they need to upgrade their version of cryptography, right? Like, normally people pip install their stuff and they go along about their day and they don't worry about updating that software perhaps ever, but certainly not until they need to do like a large scale upgrade of their environments, right? So that's an outstanding problem, to try and educate people that you need to stay on top of your cryptographic library.
Yeah, and to that end, I'm assuming that you work fairly hard to make sure that you don't make breaking changes in the API so that it is simple for people to update and maintain version parity with what's latest?
Yeah, so in general, we have a strong backwards compatibility policy. I wouldn't say we're quite as impressive as Twisted in that regard, but we definitely have long deprecation cycles where we explicitly call out things that are deprecated, including raising warnings if you use those properties for the versions after which it's been deprecated. Deprecations are somewhat rare these days. We've gotten to the point where the API is reasonably mature, and we don't want to make those sorts of changes. We don't really want to make those changes at all, because we're mostly happy with the way the API is constructed at the moment. So yeah, I would definitely say that it's almost always safe to upgrade. But certainly, if you stay on top of upgrading consistently, then you'll never be caught by surprise, because you'll always see those deprecation warnings first.
So what are some of the testing techniques that you use to ensure the accuracy and safety of the algorithms that you're using? And you mentioned test vectors, so I don't know if you can explain a bit more in detail what that means for somebody who's not familiar with some of the basics of cryptography.
Sure, absolutely. In cryptography, there's a few things you care about, and obviously one of them is whether or not, given an input of data with a key into a symmetric algorithm, do I get out the data I expect? That's effectively saying, is this algorithm written correctly? So it turns out there's ways you can write those algorithms where they look correct in most cases, but aren't always correct. And so the way that most of the authors of those algorithms deal with that these days is they come up with what they call a set of test vectors. That's just a fancy name for saying, given these variables as input, here's what I expect to see as output. And so those tend to be created as text files, usually with hexadecimal encoding for each one. So you write a little state machine that can read the files in, decode the data, and then feed it through your algorithm, and then compare the output at the end. And that will tell you whether or not the algorithm itself has been written properly. So that's our first and biggest line of defense for everything we do inside of cryptography, which is basically, if you claim that this is an implementation of this algorithm, then prove it. And that a big part of that is also the idea that as we plug in new backends, we can have confidence that those backends are correct, because we already have a library of many, many tests. So the moment you plug a new backend in and then wire it to our testing harness, you can have a high degree of confidence that that code is working properly. There's two other things that I would say matter a lot for our purposes. Like, one is the way that we handle errors, right? We need to make sure that we know how the underlying library errors when bad data is passed. And so that means that we have lots of tests that test negative cases, right? We're looking for ways to make the underlying library choke, and then we handle those cases properly. In the case of OpenSSL, it has some interesting quirks where it has like a thread local error stack, and if you don't manage that error stack effectively, you can have problems. So we have a lot of testing around dealing with that sort of thing. And then lastly, it's something we're kind of trying to expand here going forward, but have not had time to spend a lot of effort on yet, is generative testing. If you use a tool like Hypothesis, it becomes very interesting to say, well, like, given this shape of data, we expect this other thing to come out the other end. And while we may not care precisely what those bytes are, because we've already verified whether or not they work via test vectors, we do care that any permutation of data we send in via hypothesis should result in a specific like a specific length output or a specific lack of error message. So hypothesis has been very good in that regard because it allows us effectively to fuzz our underlying library.
Yeah, we interviewed David McKeever, the creator of the Hypothesis Library, a few episodes ago, and it was definitely very interesting to hear about some of the different methods that he employs for being able to generate that randomized input and validate its accuracy. And since then, I've come across a number of people who have either used or want to use Hypothesis, so it's good to hear that people are actually putting it in practice.
Yeah, I mean, Hypothesis, especially in the X509, like the certificate layer for cryptography, Hypothesis becomes very interesting because there's ASN1 parsing all up and down inside that stack. And ASN1 parsers are notoriously hard to get correct. And fuzzers are perfect for finding major bugs in those things.
So for somebody who's looking to select a cryptographic library to use in their project, what are some of the factors that they should be considering during that selection process?
The first thing I would say is, well, what are your requirements? And the requirements can be things like, management says I have to use NIST-approved algorithms, like the National Institutes of Science, Standards and Technology. And if you need to use NIST-approved algorithms, then that constrains your choice set, right? Also, it matters whether or not you're working in a world where you need to interoperate with other people. So like if you need to interoperate with some other group or some other company, then you need to be talking to them to determine what makes sense for your purposes. Because like what you think might work well might be something that's impossible for them to do in their language or so difficult that they'll have all sorts of problems. But outside of those problems, there's kind of a few high-level questions to ask, which is like, well, what is it exactly you're trying to accomplish? Like, are you trying to encrypt data? That's great, but encryption of data is too broad, right? Do you need to encrypt and keep files safe on a file system? Do you need that data to be authenticated? In general, you should assume that encryption without authentication is almost useless. But a lot of people don't necessarily realize that. So like you have to kind of go down through these pages. If you encrypt, say you want to encrypt a giant disk image on a file system, do you need to be able to seek to an offset and read the data? If so, that actually makes your problem much, much more difficult. So it's very specific to the problem set of what you may need to do. Underlying quality of the library matters a lot. And performance may matter to them as well. But the underlying quality speaks to something like, so we have a project under PyCA called Pinnacle, which is inappropriately named because in reality we bind against libsodium. That project uses Daniel J. Bernstein's primitives. Now, DJB's stuff is widely respected and actually is increasingly becoming heavily standardized throughout the IETF, but it's the sort of newer crypto that sometimes organizations aren't comfortable deploying. So while that's fantastic crypto that provides a lot of reasonably safe constructs, you may have political reasons why you can't use it. For cryptography itself, in general, we designed that to be the Kleenex of crypto libraries. The idea being that it's the generic crypto library. It's the one you would reach for by default in most cases. It has almost all the constructs you would probably need to use, but it doesn't have some of that sexy new crypto, and it will not have. It will always gain that stuff eventually, but only after it's no longer sexy, because we want those things to be reasonably well vetted primitives that have a lot of cryptanalysis, so that we have large degree of confidence that people can use them safely.
Yeah, cryptography is one of those things that everybody should want to be boring, because when things get exciting in cryptography, it usually means that somebody's having a bad time.
Yeah, exactly. Like sexy new crypto is synonymous with vulnerabilities in a lot of cases. That's not always true, but certainly to a first approximation, it's not unreasonable to think that way.
And for somebody who wants to incorporate the cryptography library into their project, what are some of the potential pitfalls that they should be aware of? And also, how much knowledge of encryption and cryptography should they possess?
Well, so as always, the more the better, but it's not required to know something about cryptography to use it. If you are a newbie to the entire discipline, then Fernet, which is our high-level symmetric encryption construct, is almost entirely bulletproof within its sphere of what it can handle, right? Again, if you try and encrypt a 30 gig file with it, you're going to have a bad time. But for small tokens and small file encryption, then Fernet is very difficult to misuse. So from that perspective, even the rankest amateur would have no problems with it. Once you start getting into needing to compose your own primitives to interoperate with something else, or trying to build your own asymmetric plus symmetric key model, then yeah, you really want to be talking to other people, asking questions, and generally being very skeptical of your own architecture, right? You should assume that anything you're trying to build yourself is utterly broken, and you should invite others to show you how it's broken. The hubris with regard to cryptographic design is a common problem. And I would urge anyone who wants to go down this path to just be humble about what you've built and ask. Be excited when people break your stuff, right? It teaches you something new about what you shouldn't have done. In terms of incorporating the library, so to do crypto safe, you have to do it outside of Python, which is something we haven't talked about yet, but that's, for the moment, let's take that as read. That means in general, you're doing it in C. And that means that if you want to distribute something that uses cryptographic libraries, you may have to force your users to have a C compiler. Now, the Python ecosystem is getting better about that, right? So we have wheels now, and on the Linux side, we even have Many Linux 1, which allows us to do binary wheels for a reasonably wide variety of Linux distributions. But that's not universal yet. In the case of cryptography, we ship wheels for Mac and Windows, so you can install cryptography very simply there. But on the Linux side, you need to have libFFI, the libFFI development headers, OpenSSL and the OpenSSL development headers, and a C compiler. And without those, you can't do it. So that's a much larger burden than just pure Python. So that's always something to keep in mind, that when you pull in a cryptographic dependency, you're significantly increasing the complexity of deploying your software.
So you touched on it briefly, but what are some of the ways that the security landscape in Python differs from that of other languages that you're familiar with? And also, what are some of the unique challenges that we face as users of Python?
So I can take that first one, or that last one first, which is the most unique challenge we face as users of Python is maybe not all that unique, but instead is shared by other languages that have other dynamic languages like Ruby, which is effectively that we don't control our memory allocation at the Python layer. So Python has a slab allocator, and then it gives you memory from that. And when an item goes out of scope, that gets deallocated in PyPy via garbage collection, or in CPython, it'll be via reference count, right? But that memory is not zeroed out, and there is no way to tell it you must zero that memory out. So that means that you do have scenarios where you may have sensitive data in RAM in ways that you will be long-lived, even though you want it not to be. So there's basically nothing you can do about that in Python land or Ruby land or JavaScript land unless you reach explicitly down through the FFI layer and talk to C only, which can be very challenging. So those are things that we have to deal with as Python users. We have to recognize that there are things Python's very good at, and there are things that Python's not so good at. And this is one of them. Now, in general, while this is a thing it's not very good at, it turns out that the threat models for compromise in most applications, it doesn't really matter. Like, if somebody is capable of reading the memory of your process, they probably have a persistent presence on the machine, and that means they can read the memory. They could read the C memory of your process before it was zeroed anyway, and therefore it wouldn't be that hard for them to extract keys. So this is one of those ones where, like, it is a problem, but how much of a problem it is very much depends upon your domain.
In what ways the security landscape in Python differs from that of some of the other languages that you're familiar with?
Python actually has it pretty good in the security, like in terms of general security, right? We have, while the SSL module is not the greatest in the world, thanks to the efforts of Alex Gaynor and David Reed back when Python 2.7.9 came out. We validate host names by default. We have people like Corey Benfield working hard on requests and making sure that requests has sane defaults that result in good validation of things. We have the PyCA projects providing reasonable cryptographic primitives on that front. And in general, we have a pretty vibrant ecosystem of people who care about this stuff working. Sometimes that's not true in other languages, or in other languages, you end up with things living in the standard library that kind of suffer over the long term. One thing I do very strongly believe is that cryptographic libraries do not belong in the standard library because they need to be more agile. They need to be capable of changing. And while that is unfortunate from a stability perspective, it's the reality of the world, right? And it turns out that in the past, when we've been complacent about allowing software to be upgraded, we ended up with the debacles around TLS, where it became very difficult to deploy TLS 1.2, and it took the concerted effort of multiple multi-$100 billion companies to actually push the state of the art forward.
And going back to what you're saying about zeroing out the RAM and not having control of the memory management in terms of ensuring that the secrets that are held in memory are properly disposed of. Would something like Cython be a viable option to control that level without necessarily having to drop all the way to full C code?
That's an extremely good question, and I don't actually know the answer to that. So if Cython allows you to read strings from the file system without ever actually making them into a Python object, or while making them a Python object that you explicitly control the memory of, then yes. If it doesn't allow that behavior, then no, it won't help.
Well, if anybody knows the developers behind Cython, then feel free to ask them that question, and I may do so myself. So what are some of the fundamental aspects of encryption and cryptography that you think that every developer should at least be aware of, if not intimately familiar with?
So the single biggest thing I think developers should be aware of is what's good randomness, right? It's very common for people, especially when they're picking up a language like Python, to think that the way that they should get their randomness is by typing import random. Unfortunately, random.randrange and things of that nature are actually a Mersenne twister instance that's a global singleton. Now, that's perfectly fine and, in fact, desirable in certain scenarios, right? Randrange is great if you want to seed your Mersenne twister instance so that you can get like randomly generated world, right? So if you're making a game, it's great to be able to seed your random generator explicitly so that you can have reproducible, quote, randomness. However, it's really, really bad for cryptographic purposes. So if there's one single thing I would tell developers to know, it's when you're generating a key to be used for cryptography, that data should come from os.urandom. It should not come from anywhere else. Other than that, on the encryption side, key management is obviously one that I would say matters a lot. Understand how to keep your keys in safe places and not reuse keys unless you need to reuse keys. And then kind of finally, when you're doing encryption, encryption alone is not sufficient. You need some form of authentication. If you don't have authenticated data, essentially, if you don't have some guarantee via HMAC or some sort of tag that says this ciphertext is what I expect it to be, then that data can be tampered with, even when it's encrypted. There's a very interesting and very simple attack that can be performed where if you know that if you imagine you have an encrypted payload that's a GET request, it is trivial to say, I'm going to change that G into something else. Like you can change the letters GET into any other 3 letters that you want to without ever being able to decrypt it because of the nature of the way cryptography works. You just have to XOR some values and you're done. So that's an attack that will always work 100% of the time unless you have authenticated encryption. So never encrypt without authenticating.
And if anybody wants to learn more about security and encryption, what are some of the resources that you would recommend they take a look at?
A friend of mine, LVH, wrote a free book that's called Crypto 101, and I believe there's a link that you're going to be providing for that. That would be my primary suggestion for starting out. Crypto 101 is a fantastic resource. From there, it's kind of that'll give you a good grounding in various areas of cryptography, and you can kind of spread out and do what you're interested in. If you're interested in breaking crypto, then Matasano wrote the Crypto Pals, which is a set of, I think it's up to 7 sets now, of cryptographic problems where you are tasked with breaking various crypto things, where there's bugs in the implementation or mistakes made, and then your job is to recover the keys or recover the message without having access to hypothetically what you need. So that's a really, really good way to learn additional crypto, including practical cryptographic engineering concerns. Because ultimately, if you're going to be a developer working in cryptography, you care more about how people might screw up than making new cryptographic primitives.
Are there any topics that you think we should cover before we close out the show?
The only other thing I haven't covered would be that the PyCA has kind of 3 major projects, which is cryptography, PyNackle, and PyOpenSSL. And through a quirk of history, one of the main reasons that cryptography is actually based on OpenSSL is because PyOpenSSL uses the underlying bindings to do its work. So PyOpenSSL is actually a pure Python project these days. It just depends on cryptography to do all the FFI. However, those 3 projects can always use additional contributors. While I say that Python in general is a healthy and vibrant community, and we have lots of people who care about crypto, we do have a shortfall of people who are willing to go through the amount of rigor and effort it takes to seriously contribute to these libraries. So I would urge anyone who's interested to please reach out, file issues, ask questions, hop on IRC. We're happy to help people get up to speed. It's definitely difficult to become a major contributor, but for the sake of Python in the long term, we definitely need more people.
All right. Well, for anybody who wants to get in touch, I'll ask you to send me your preferred contact methods, and I'll add those to the show notes. And with that, I'll move us to the picks. And my picks today are, first one is an email service called Migadoo, which is a company out of Switzerland that provides a hosted email platform where you can host your own email domain, similar to what you can do with something like Google Apps, but at a much lower cost. And it's a one low fee for being able to host as many different domains as you want. So I've started using that for one of my domains, and I'm working on moving some of the other ones over. So I've got a link in the show notes that'll actually get you a 10% discount on any of their plans. So if you click that and check it out, then you'll get a few bucks off from them. And my other pick today is a board game called Castle Panic that I picked up recently to play with my son. And it's just a really fun tower defense style board game where you are working together with the other players to try and defend the castle tower against all of the monsters who are coming in from the forest. And so in order to win, you have to outlast all of the monster tokens, and the monsters are all trying to destroy the castle. So it's a lot of fun, has some fun strategy, and it's just an enjoyable all-around game to play. So with that, I'll pass it to you. Do you have any picks for us today, Paul?
Sure. So since I'm so self-absorbed, I have to hype two additional projects I might have. One of which is Frinkiac, which is frinkiac.com, which is where it allows you to search for Simpsons quotes and has over 3 million screenshots that you can choose from. And then the other one would be Morbotron, which is the same thing only for Futurama. So those are little labors of love I do on the side when I'm not working on cryptographic things.
All right. Well, it's good to hear that you're making the world a better place as well as a safer one. All right. Well, I appreciate your time today. It's definitely a very interesting set of projects, one that I'm glad that I know a little bit more about, and one that I hope that other people will be able to benefit from. So I appreciate your time, and I hope you enjoy the rest of your day.
Thank you very much. Anytime.